In this video we discuss derivatives of power functions. What is a power function? A power function has the form a times x to the b, where a and b are real numbers. Some examples of power functions are obvious. Something like p of x equals x squared is a power function. So is q of x equals 5 times x to the fourth. However, the power doesn't have to be a whole number. R of x equals x raised to the 1/3 power is also a power function. So is y of x equals x raised to the -2. In this class, we are interested in taking the derivatives of functions. One of the most basic derivative rules we need is called power rule. There are a few different ways to write power rule. One way is to look at a function of the form x to the n. Then the derivative of x to the n is n times x raised to the n minus 1 power. There is an alternate way where we consider a constant multiple in front. If we have a times x raised to the b, then the derivative is a times b times x raised to the b minus 1. This is really a combination of the previous rule with constant multiple rule. Whichever way you prefer to think about power rule, it should be straightforward to apply. Let's look at some examples. When we look at p of x equals x squared, the exponent is 2. We pull the 2 in front, then subtract 1 from the 2 to get an exponent of 1. We don't usually write an exponent of 1, so the derivative would just be p prime of x equals 2 times x. Q of x is equal to 5 times x to the fourth. Then to take the derivative we will just pull down the 4 and multiply it by the 5. We subtract 1 from the 4 in the exponent to give q prime of x equals 20 times x to the third. Way with non-integer powers. If r of x is equal to x raised to the 1/3, then r prime of x would be 1/3 times x raised to the 1/3 minus 1. There is another way to rewrite this algebraically that we will see in a few minutes, but for now let's just focus on applying the basic rule. If y of x is equal to x raised to the -2, then y prime of x is equal to -2 times x raised to the -3. This is another one that we would probably rewrite, since we don't usually like negative exponents. However, for now let's just focus on applying the rule, and look at how to rewrite the expression later. Mathematicians have developed some conventions for writing expressions involving powers. Because of these conventions, there are ways of writing power functions that don't immediately fit the easy form we just saw. One of these rules involves rewriting roots in terms of fractional exponents. The nth root of x is also written as x raised to the 1 over n power. Here are some examples of this. The cube root of x can be rewritten as x raised to the 1/3 power. The square root of x can be rewritten as x raised to the 1/2 power. Another example involves negative exponents. When we have 1 over x raised to the n, this can be rewritten as x raised to the -n power. For instance, 1 over x cubed could be rewritten as x raised to the -3 power. 1 over square root of x could be rewritten as 1 over x raised to the 1/2, which can be rewritten as x raised to the -1/2 power. 7 times x raised to the -4 could be rewritten as 7 over x to the fourth. Notice that only the x is being raised to the negative power, so only it goes to the denominator. The 7 isn't being affected by the negative exponent, so it gets to stay where it is. Another common pattern is when you have two terms with the same base, but different powers, and they are being multiplied together. We can combine this into a new expression by adding together the two exponents in each term. In words, we would say that x to the a times x to the b is x to the a plus b. For example, if we had x cubed times x squared, this would become x to the 2 plus 3, which simplifies to x to the fifth. Finally, if we raised a power function to another power, the result has an exponent equal to the product of the original exponents. In other words, if x to the a is then raised to the b power, the result is x to the a times b power. For instance, if we take x squared and raise it to the fifth power, the result is x to the 10, since 10 is 2 times 5. If we are taking the square root of 7 times x raised to the fourth, then we rewrite the square root as the expression raised to the 1/2 power. This is 7 raised to the 1/2 power times x raised to the 4 times 1/2 power. This simplifies to square root of 7 times x raised to the 2. Another example is if we have 3 over x to the fifth, raised to the 4th power. Again, both the 3 and the x to the 5th need to be raised to the 4th power. This becomes 3 to the 4th power over x to the 20th power. We can use these patterns to look at some more examples of derivative problems. If p of x is equal to 3 times x squared, what is p prime of x? We bring the 2 down and multiply it by the 3 to get 6. We subtract 1 from x to the 2 to get x raised to the 1. The result is p prime of x equals 6 times x. If q of x is equal to x raised to the 1/7, what is q prime of x? The answer is q prime of x is 1/7 times x to the 1/7 minus 1 power. This is 1/7 times x to the -6/7 power. If d of x equals the fifth root of x squared, What is d prime of x? First we rewrite d of x as d of x of the 2 raised to the 1/5 power, which becomes x raised to the 2/5 power. Then we apply power rule to see that d prime of x is 2/5 times x raised to the 2/5 minus 1 power, which is 2/5 times x to the negative 3/5. If v of x is equal to x to the 4th times 3x squared, what is v prime of x? We use rules of exponents to combine this into v of x equals 3 times x to the 6th, so v prime of x is 18 times x to the 5th. We needed to simplify it first algebraically to find the derivative.